At the end of Chapter 10, we discussed the phenomenon of resonance, in which large amplitudes of vibrations can occur in mechanical systems when driven at their fundamental frequency of vibration. For example, resonance can occur when a vibrating force acts on an object of mass m that is attached to a spring whose spring constant is k. In this case, there is one natural frequency, f0, whose value is given by 1 over 2 pi times the square root of k over m. Resonance also occurs when standing waves are set up on a string or in a tube of air, as we saw in Chapter 17. The string and tube of air have many natural frequencies, one for each allowed standing wave. As we will now see, a condition of resonance can also be established in a series RCL circuit. In this case, there is only one natural frequency, and the vibrating force is provided by the oscillating electric field and is related to the voltage of the generator. To help us understand resonance in an electric circuit, let's revisit resonance in a mechanical system first, such as a mass attached to a spring oscillating back and forth on a frictionless surface. The total mechanical energy of the mass is the sum of its kinetic and elastic potential energies. As the mass moves, it trades elastic potential energy for kinetic energy and vice versa. At positions of maximum displacement, or when the spring is stretched or compressed by the maximum amount, the kinetic energy of the mass is instantaneously zero, and all of its mechanical energy is due to elastic potential energy. Likewise, when the mass moves back through the equilibrium position, i.e. when the spring is neither stretched or compressed, its elastic potential energy is equal to zero, and the mass's total mechanical energy is purely kinetic. A similar oscillation occurs in an electric circuit containing an inductor and capacitor. Here, the electrical energy in the circuit is stored in the electric field between the plates of the capacitor, as well as in the magnetic field that develops within the inductor. If we consider the moment when the capacitor is fully charged, and no current is flowing around the circuit, then all of the electrical energy of the circuit is stored in the electric field between the plates. As the capacitor discharges, the electric field between the plates decreases, while a magnetic field builds up around the inductor because of the increasing current in the circuit. The maximum current, and thus the maximum magnetic field, exists at the instant when the capacitor is completely discharged. The circuit's electrical energy is now stored entirely in the magnetic field of the inductor. The voltage induced in the inductor keeps the charges flowing until the capacitor again becomes fully charged, but now with the reverse polarity. Once again, the energy is stored in the electric field between the capacitor plates, and no energy resides in the magnetic field of the inductor at that time. Thus, an AC circuit can have a resonant frequency, because there is a natural tendency for energy to shuttle back and forth between the electric field of the capacitor and the magnetic field of the inductor. Recall that the current in an RCL circuit is given by the following, where Z is the impedance. As the figure shows, the RMS current is a maximum when the impedance is a minimum. The minimum impedance has a value of Z equals R, and this occurs when the frequency is F0, such that the inductive and capacitive reactance are equal, or 2 pi F0 times L is equal to 1 over 2 pi F0 times C. This result can be solved for the frequency F0, which gives us the resonant frequency. Note that the resonant frequency depends on the values of the inductance and capacitance, but does not depend on the resistance. The resistance does have an effect on the response of the circuit as the figure shows, but its value does not affect the resonant frequency. When the resistance is small, the current frequency graph falls off suddenly on either side of the maximum current. When the resistance is large, the fall-off is more gradual, and there is less current at the maximum.